For the longest time, rest and motion has confused man. And let's see why that's the case. Here I have a 2 kg weight. It's the end of a dumbbell, actually. I'm going to place this weight on this glass sheet. And now, as most of us can relate to from daily life, this weight is right now at rest. And we know that it's not going to start moving on its own. If I have to make him move, I have to mess with him in some way. I have to apply some sort of a force to change his state from rest to motion. Let's do that. Now he starts to move. But then what we see is that the moment I remove the force, immediately he comes back to rest. And if I have to keep him moving, I have to keep on pushing him with the force. And again, the moment I remove the force, he's back to rest. Greeks like Aristotle did these kind of experiments, and they came to the conclusion that all objects like to be in the state of rest. Rest is natural. They don't like the state of motion. Motion is unnatural, which is why if I have to change something from rest to motion and I apply a force, the moment I remove the force, because the object does not like to move, it immediately wants to come back to rest. So rest was natural, motion was unnatural. This prevailed for many, many centuries until the likes of Galileo and Newton came along, and they hypothesized something totally different. They said, hey, wait a minute, there is actually something else happening here. The reason this object, once it's starting to move, immediately comes to rest is not because it does not like to move. It's because of something called friction, which was unknown to the Greeks at the time. What their hypothesis was is that when an object is moving over another surface, because of this contact, they are kind of getting in each other's way. There's a rubbing that's happening. And because of that, a force is produced, which is basically acting in a direction opposite to the direction of motion of the object because of this contact, because they're in the way. And that force causes the object to slow down and stop. So the object is not stopping because it wants to stop. It doesn't have a choice because there's a force acting. Now, we can't really see this force, right? So everybody laughed at them. They, what are you saying, bro? No such thing. So we have to now do an experiment to prove that. Let's see what experiment we can do. This is where it gets a little crazy. Now, this is the crazy experiment that we're going to try. This, as you can see, is just a simple hollow metal can. It's a milk can. Now, what we've done in this can is we've packed it with about 2 kg of dry ice. Dry ice is solidified carbon dioxide. Carbon dioxide solidifies at a temperature of minus 80 degrees Celsius. So this stuff is really, really cold. Now what happens when I pack this with dry ice, because the room temperature is obviously much higher than minus 80, the dry ice starts to vaporize, producing carbon dioxide gas. And as the gas pressure builds up, this gas has to go somewhere, like gas in all aspects of life. It has to go somewhere. Now where does it go? Much like a pressure cooker, the gas pressure builds up and now has to go somewhere. For it to go out, we have provided a small hole at the bottom of this can. So as the gas pressure builds up, the gas now ejects from the hole at high pressure. Very similar to what happens in a pressure cooker. As the steam builds up, it has to go somewhere and push, it goes up. And because of its force, the weight on top of the cooker levitates. That's what we're going for here. So what we'll now see is when I place this can on the glass sheet, for the first few seconds, the gas pressure hasn't built up yet. So the can is still fully touching the glass sheet. But after a few seconds, when the pressure builds up enough, like a pressure cooker, the gas comes out. When the gas comes out with great pressure, it causes the can to levitate above the glass sheet, thereby making the contact between the glass sheet and the can almost zero. Therefore, no rubbing, therefore no contact, no friction. And then we'll repeat the experiment. We'll give it a slight force, and then we'll see, is it indeed moving for a much longer time, or does it still stop, like what happened to the earlier weight? And let's see who's right, Aristotle or Galileo. Placing it here, as you can see right now there's no pressure, so it's still stopping. Now I'll keep it here, wait a few seconds. Now you see the levitation has happened, so it's already just moving. Now let's see what happens. Slight force to get it to start moving. Looks like Galileo and Newton are winning this. There's no friction now, nothing to stop it. So once I give it an initial force to start it from rest, it then maintains its motion. Doesn't become faster, doesn't become slower until somebody stops it. Now if I have to stop it, I have to apply a force. This is what the friction was doing. And therefore we can see that Galileo and Newton were on the money. This was finally codified by Isaac Newton as his first law. He said, both are true. What are the two things which are true? If an object is at rest, and if you don't apply any force on it, it will stay at rest forever. That much was okay. Even we were okay with that. But now the second part is the kicker. Same way, if an object is moving, and if there's no force acting on it to slow it down or stop it or do anything, it will just maintain its motion forever and ever and ever. And for it to keep moving, you don't have to keep on pushing it, because there's nothing stopping it from moving. There's no friction. So both are true, which means rest and motion are equally natural. It's not like the body likes one over the other. This is now what we know as Newton's first law of motion. Now, an interesting implication or an effect of Newton's first law. Here we have, again, our weight. I want to keep this on the table. Now, we know, or we've been told in our science classrooms, that our planet Earth is floating around in space, and it's not just sitting in space. Apart from revolving around the sun, at wherever it is, it's spinning consistently about an axis. Now, the question is, how is it going on spinning forever and ever and ever? Because if we try to do that experiment on Earth, if I have this dumbbell weight over here, and if I have to make it spin, I have to do something, right? And again, the moment I stop, it stops spinning. So the natural question we had was, how is the Earth going on spinning? Now, our understanding of Newton's law helps solve that. Because what we realize that in outer space, much like in our cruiser experiment, there is nothing around the Earth. There's no material. So basically, the Earth, when it spins, it's not rubbing against anything. There's no friction. So what we realized is when the universe was first formed, boom, the explosion happened, and the Earth, when it was formed, was already spinning. Now it's already spinning, and there's no friction. So there's nothing to slow it down, no force to slow it down and stop it, and therefore it will just keep spinning forever and ever and ever until something stops it. Newton's first law. Now we can show that with our cruiser. Now what I'll do is I'll again place it on the table. For the first few seconds, levitation won't happen. So it will still be in contact. Therefore, it will be very similar to this. If I spin it for some time, it should stop. But now, if I wait for a few seconds, it levitates. And now there's no friction, or very little friction. And now it will behave like the Earth in space. As you can see, it seems to have no problem just spinning in place until something stops it. So Newton's law then started to explain why the Earth is quite happy to keep on spinning. For our final experiment, we'll be exploring another crazy implication of what we have discovered about Newton's first law. And let's recall what we've discovered. We have seen now that if an object is at rest, it will stay at rest forever until you mess with it by applying a force to change its state from rest to motion. But Newton discovered that the second part also is true. Once an object is moving, it will keep on moving until you disturb it with some force to stop it. If you don't apply any force, it will just keep moving on its own and maintain its motion. So both are true. This last experiment is a trippy demonstration of the rest part. So let's look at what we have here. I have a smaller version of the glass sheet, and I have my trusted 2 kg weight. So what I'm going to do now is when I keep this weight on the glass sheet, as expected, there's full contact between the weight and the glass sheet. So now what's obviously going to happen, if I use my hands and I apply a force on this glass sheet to pull it and push it back and forth. So I'm applying a force, and because of my force, the sheet which is at rest now starts moving. So what we must expect to see, because the weight is also fully touching the glass sheet essentially acts as a conduit. It will transfer my force effectively onto the weight and also pull the weight along back and forth. So what's happening to the weight? It's at rest, but now a force is acting on it because of my hand through the glass sheet, and that force is obviously going to change its state, causing it to start moving. Let's see and make sure that that's exactly what's happening. As you can see, this is something that we can all try at home, and this is something that is not particularly fascinating. We'll get there. Now, having seen that, we'll keep this back here, or we'll keep it here rather. Now let's recall what happened with our cruiser and understand it in the context of Newton's law. If I place the cruiser on this sheet, For the first few seconds, very similar to this weight, the cruiser has not yet started levitating because the gas pressure hasn't built up. So therefore, there will be full contact between the cruiser and the glass sheet. And therefore, just like the weight itself, when I pull the glass sheet, because the cruiser is touching the glass sheet fully, it will also respond to my force and it will start moving because of my force. But after a couple of seconds, just a few seconds, once the gas pressure builds up enough, now the cruiser is slowly a bit levitating above the glass sheet. And therefore, the contact between the glass sheet and the cruiser is now pretty much zero. When the contact is zero, the glass sheet has no way of applying a force onto the cruiser to cause its state to change from rest. And therefore, if that's going to happen, what we must expect to see is crazy. What we must now see is the cruiser just floating almost in the same place, while the glass sheet and all this weight and everything move back and forth because the cruiser is not receiving any force. And because of that, if it was originally at rest, it will stay at rest. And that's a pretty crazy outcome. Let's see if it's right or wrong. So, we have our cruiser again. Now, I'll quickly do it first before it levitates. And you can see it's moving just like the previous weight. Now, give it some time, have it levitate. I'll know it's levitating because once it levitates, it starts to just hover about because of minor atmospheric winds, etc. Now it's hovering. And now let's see. It's at rest. And there we go. Totally oblivious to the chaos happening underneath because it stays at rest because there's no force acting on it. And this is pretty darn crazy. Newton's first law.